is going to be a game changer in the life of future structural engineers who are present here in large numbers. I want to tell them that this is going to be the first logical step from current regulation based design towards performance based design of structures, which will definitely, besides other things, give more power to structural engineers as they will be able to set the building's structural performance in the process of design. So let's get started. But up first, it is my pleasure to introduce some people because of whom we are enjoying this wonderful and highly technical session. I think let's begin with Engineer Jain Kulkarni first. It's my great pleasure to be the one who is introducing him. And a small note before we start off, please put your questions in the QA box. Am I right? Can we show that slide, please? This is very important. Please put your questions in the QA box and not in the chat box. All of us are seasoned people on webinars and Zoom, but this is just to remind you. So yes, let me introduce Engineer Jain Kulkarni. Jayan Kulkarni is the founder, member, and managing director of Epicons Consultants. As far as his qualifications, as you can see on the screen, no need to mention his qualifications as a BE and as a master's. Areas of interest also you can see on screen. And yes, I would like to mention here that this culture of knowledge and sharing of knowledge that he has started with Epicon's Friends of Concrete is something really extraordinary. Can we have the next slide, please? Epicons has been responsible for all these extremely interesting, beautiful, and cutting edge structures. And the buildings that you see on screen are just a mere handful of their work in so many decades. Next slide, please. So, more than 8,500 projects given to the nation, and how great is that? Apart from different typologies, different technologies, different collaborations with so many architects and techno savvy people, this culture of knowledge that EFC is spreading is something that I, for one, am honored to be part of. Let's move on. Next slide. Now, this is the time in the webinar when we begin with a brief introduction of EFC, that's Epicon's Friends of Concrete. And Jain sir, I hand over to you to do this.
Good afternoon, everyone. I would like to introduce Epicon Friends of Concrete. It is a knowledge sharing platform since 1999. It works under umbrella of Epicons Consultant Private Limited, which is ISO 9001-2015 certified company. One of the well-defined objectives of the company is imparting technical knowledge to society at large and interested parties. Next. Even though we got certified 12 years back, our inspiration goes back to late engineer A.P. Remedios. He's our philosopher friend and guru. He motivated us to conduct such workshops. Next. But I must tell that after that and before that also, the inspiration starts from my teachers, Dr. Vin Gupchup, who is very much present for opening remarks, Professor Sundaram, Professor Gargi, who is still part for many webinars, workshops. Sudhir Jain and Murthy, they were the person who introduced us to earthquake engineering. And of course, A.C. Basu has a remarkable contribution in all our activities. Next. EFC has conducted 84 workshops in the last 25 years and 46 webinars in last 4 years. We started webinar series since lockdown through our unit Epicon Friends of Concrete dedicated to training. 2 photographs of workshop 55 and 70. EFC is an humble effort to create knowledge sharing platform and develop facility for continued education for practicing structural engineer, corporate consultant, government, semi-government authorities, architects, builder, and of course, faculty and student. Next. Today we are at webinar 147, Pushover analysis of RCC building, being conducted by none other than Professor Dr. Yogendra Singh. And we first time will be trying after a long break a physical workshop on 22nd March, rainwater harvesting, which is the World Water Day on 22nd March. Next. Now, let me introduce to my team, just by name, apart from myself, Anand Kulkarni, Ravindra Deshpande, Arvind Parekar, architect Parashar Mugi, and engineer P.P. Pandey are the team member, director, and unit head. They contribute a great whenever we conduct any workshop or webinar. Next. And with this, I thank all my staff because it is not only the team of 6, the entire staff join hand for conducting any events like this. Thank you.
Thank you, Jain sir.
Haan.
Yes. Friends, we shall be beginning with some opening remarks by none other than Dr. Gupchup. But before that, a little about my little company, which is called Wide Angle Forum. I'll just quickly tell you about it. We are a company which is based in the uh, organization of events and many other things in the areas of design, lifestyle, and construction. The first, as you can see, our flagship brand, which is organizing events like presentations and so on and so forth. Next. We also have a Design Vista magazine, which is a national level magazine, which is circulated all over the country. Next. Yes, we have an Aspire Academy where we help students gain employability, help in grooming. And I'm very honored that we are lucky enough to be part of this webinar thanks to this platform. We also have study tours where we all sit in a bus and go to see interesting people and places. Next. Yes. And we also have a book club. We meet interesting people. We love to meet new people from all these fields. And we like to call ourselves one of the think tanks of society. So we are Wide Angle Forum. Would love to connect with all of you. We are based in Pune, but working all over. Thank you so much. Very honored to be part of this webinar. And let's move on. So friends, now this is the stage where we actually get to the nitty-gritty of this webinar. But before that, it is important to introduce some very nice people to all of you here. It's my honor to first begin with an introduction, a very short introduction of Dr. Gupchup, who we will be inviting to give the opening remarks. Interestingly, Dr. Gupchup also has a Wikipedia page dedicated to him. And to put a lot in a summarized manner, he is an educationist, academic, researcher, and considered an expert in the field of civil engineering and structural engineering. A bachelor from the VJTI Bombay 1958, subsequently did a lot of dabbling in many fields, was the pro vice chancellor of the University of Mumbai till 1995. All of us know that. Was the chairman of the National Board of Accreditation, which is a very, very important body for the AICTE. Along with this, Dr. Gupchup, I must mention specifically, has been extremely active in the field of technical education for over 35 years and has provided leadership to the state of Maharashtra, has contributed to various aspects of the development of technical education. We all know how important this is from the point of perspective of India being a global leader. He's a traveler also and has authored numerous technical papers. So how wonderful it is to have somebody like Dr. V.N. Gupchup being present here at this intense session. Dr. Gupchup, it's great to have you. And on behalf of every single person sitting here, it's an honor to welcome you and thank you for coming here and interacting with all of us. If it's okay, I would like you to give the opening remarks and then we shall move on to the introduction of the directors of Epicons. Over to you, sir.
Thank you, Priya. It's indeed a great pleasure for me to join this 147th webinar, which is being organized by Epicons Friends of Concrete, Jan Kulkarni and his colleagues. Jan has been a student of mine, so I feel extremely proud to be associated with this program. I think Jan's interest in concrete as a construction material, reinforced concrete structures, pre-stressed concrete structures, stem from his student days. His master's degree thesis at VJTI was concerned with high frequency vibration and chemical admixtures and effect of these on high strength concrete. So I think he's carried on his interest and passion for concrete as a material and also the structures. And it's really wonderful that he has been able to generate and keep up interest of civil and structural engineers in this field. We must welcome Dr. Yogendra Singh from Roorkee. Sir, I have visited Roorkee many times before. I haven't had the pleasure of meeting you, but I used to meet Professor Nayak and others long time ago. Actually, nonlinear dynamic structural analysis subject to seismic effects is a very complex, very complex phenomenon, complex exercise. And we're having here Dr. Yogendra Singh to talk to us about pushover analysis, which according to him is a simpler way of dealing with the problem. So with all that, I think I thank you all for being here. Thank you, Dr. Yogendra Singh. Thank you, Jan, and thank you all the colleagues, Jan's colleagues at EFC. Thank you very much.
Thank you, Professor Gupchup. It was really nice to remember your days as a mentor to a student who is now a senior individual himself in this field. That was really sweet. And now, friends, let's move on. If we can have the slides of the directors, that will be great on screen. Because at this point, I will be introducing all of you to the three people who are key to this webinar happening. And it's my great pleasure to introduce, firstly, Engineer Anand Kulkarni. He's a director of Epicons Consultants Private Limited, graduated with a specialization in structures in 1987. 37 years of extensive experience in structural design, has worked on a diverse range of projects, including residential, commercial, malls, hotels, and industrial buildings. And as the next slide will show you, specifically design of tall buildings. So how glamorous these look, but all of us, especially all you wonderful people sitting there, know the extreme complexities that go into every inch of these buildings. So we would like to credit him with many of these wonderful buildings. And moving on to the next director, whom I would like to introduce is Engineer Arvind Parurekar. Again, has conducted many training programs on NDT. He's said to be an expert in this particular area. For last 21 years, he's a director at Epicons and has also been appointed auditor and serves in a number of various capacities specifically related to NDT and repair and rehabilitation. To go on to his expertise, his areas of specific interest also, NDT and structural assessment department is being handled by him. And it will be safe to say that he's a geek in all these things, just the way a computer geek is a geek. So this is about Arvind Parurekar. And let's move on to Engineer Ravindra Deshpande. He's particularly responsible for responsibilities, few of them being detailed engineering, repair, rehabilitation, retrofitting, and he's an expert in that. So, of course, an ME from VJTI has been a director at Epicons, and for the past 28 years, he's at Epicons. Has also acted interestingly as an external examiner for postgraduate students of Mumbai University. I'm not sure if he was a benevolent examiner or a brutally strict examiner. That's for him to say. Maybe you can add it somewhere in your talk later on. But jokes apart, these three directors, we welcome you and we thank you also for being part of this webinar that all of us are going to be part of. Next. So yes, friends, I would request Engineer Ravindra Deshpande to give the preamble for this evening. Please begin.
Thanks, Priya. I am audible?
Yes, sir.
Okay. Good afternoon and welcome to Dr. Yogendra Singh, Dr. Gupchup. He was my teacher as well, and all the participants on the behalf of Epicons Friends of Concrete. When we were looking for a topic for today's webinar, what we realized was that Dr. Yogendra Singh has already covered most of the topics which are related to seismic analysis, design, and detailing. But one of the topics which we felt was worth repeating for the benefit of many of the structural consultants was pushover analysis. As we all know, performance-based design is rapidly becoming the need of the hour because of various considerations. Our tall building code recommends nonlinear analysis for code exceeding buildings that they have defined in the table 11. For complying this requirement, pushover analysis, which is a tool for nonlinear static analysis, is also of great help. A nonlinear static analysis can predict the failure mechanisms or detect the possibility and location of premature failure more accurately, since it considers inelastic behavior of the structure. In today's presentation, Dr. Yogendra Singh will not only give the theoretical background of pushover analysis, but also demonstrate step-by-step procedure through a real-life example. I'm sure it will be very helpful for the participants. He will also try to answer as many questions as possible at the end of the session. With this, I hand it over back to Priya. Thank you.
Thank you, Ravindra sir. Friends, just drop everything that you're doing. Let's all concentrate here. A few things to remind you before we begin. Similar to what in a live function, they never forget to remind you to keep your mobiles on silent. They never forget to do that. So it's my job to remind you about a few things before I introduce Dr. Yogendra sir. First, as we all know, please put your questions in the QA box and not in the chat box. Secondly, as far as the time flow is concerned, we'll be having a part one of the presentation by Dr. Yogendra Singh. Then we'll be having a very small tea break. And then, as you all know, a demo on real life building. Then we begin with the part two. And then definitely we'll be having very nice Q&A session, which probably will be the nice finale to the intensity of this workshop. And yes, we shall be sticking to time. So I request all the speakers also to stick to time. Now, at this point, I would love to introduce Dr. Yogendra Singh. Currently, as all of us know, Dr. Yogendra Singh is Professor of Earthquake Engineering at IIT Roorkee. He's a BE in Civil Engineering from IIT Roorkee, and he's back at his alma mater. How wonderful is that? Yogendra sir will, of course, be telling you more about actually everything that he does, but it's my job and my duty to just give you a small gist of his various achievements and his curriculum vitae so far. So, about 30 years of research and teaching experience has also included the fact that he has guided 17 PhD students, perhaps more. So, how wonderful to be an educationist, an engineer, a technocrat, a guide, and a mentor to the future next and leave behind this legacy of knowledge and technology. He's also a very prolific author, has shared his knowledge in as many and perhaps more than 85 research articles in various journals, a member of several expert teams, of course, for post-earthquake damage surveys. He was a convener of the BIS expert group on performance-based seismic design of structures, and of course has collaborated with so many organizations, platforms, associations on a truly, truly global basis. Dr. Professor Yogendra Singh, we from Epicons Friends of Concrete, Wide Angle Forum, and all the people who are sitting here are extremely grateful and very happy to have you. Please begin and let's enjoy whatever we have to learn from here. Thank you and over to you.
Thank you, Priyaji, for nice introduction and such nice words. And thank you, Professor Gupchup, for being here. Your presence, sir, is very encouraging to us. And before I start, I think I should convey my gratitude to Mr. Kulkarni and his team. They are taking all the pains, and I'm finally coming and delivering, but all the background work, and that is also a lot of work they are doing. So to start, I will share my screen. I guess my screen is visible.
Yes, sir.
Okay. So I think the screen is visible and I'm audible. So as introduced by the previous speakers, today we are going to talk about pushover analysis of RCC buildings. And this is the simplest method for nonlinear analysis. And we have covered nonlinear analysis procedures in detail earlier. But in earlier talks, we tried to cover all different methods of nonlinear analysis, and that became quite heavy for our audience. So this time we thought that we will focus on a smaller topic, a smaller portion of the nonlinear analysis. That is the initial step, the first step, and this will uh, this will work as a background for the further steps like detailed nonlinear dynamic analysis. So pushover analysis, which we also call nonlinear static method. So we can divide analysis procedures into two categories based on the behavior of the material, that is linear and nonlinear. And then we can also divide based on the dynamic characteristics of the structure. We can divide those into static and dynamic. So all the four combinations are possible. We can have linear static, linear dynamic, nonlinear static, nonlinear dynamic, and nonlinear static, that is pushover analysis, which we are going to discuss today. This is the simplest and of course approximate because it is simplest and the first method which one can learn to have an idea of nonlinear behavior of structures. Now, why we need to learn nonlinear behavior? So let me tell you that the design philosophy for earthquake resistant design is different than what we are using for other loads. In case of earthquake, we are designing our structures to get damaged. Because if we want to design our structure not to get damaged, the design is going to be uneconomical. It will be costly. We can do it if we so desire. If we are designing, let us say, a hospital building, which we want to remain functional after an earthquake, perhaps we will like that the damage should be minimal, practically no damage. So that is possible, but the cost will be high. So we can decide how much damage is acceptable to us as owner, as builder, or as the designer. And then we can target that damage to achieve in our design, and that design is called performance-based design. Now, when we are designing our structure to get damaged, naturally its behavior becomes nonlinear. And so far, whatever methods we have been using in our industry, those are based on linear analysis. So linear analysis we can perform based on certain assumptions. And those assumptions are available in the code in the form of do's and don'ts. So if we follow those do's and don'ts, then only that linear method is applicable. And even if we are using that with all do's and don'ts followed faithfully, even then we do not know how exactly our structure is going to perform during earthquake. So if you show you schematically what we are doing in design. So any design consists of estimation of two parameters, the demand and the capacity. And we have to keep capacity higher than the demand. So in case of earthquake, the demand is given by response spectrum. Usually it is given by time history also. In case of time history analysis, we will be using time history. But most of the codes, they provide response spectrum as the parameter to estimate demand for design. So this blue curve at the top, you see, this curve is estimation of demand. So this is representing the expected response spectrum at any site. This can be obtained from code, or we can do a seismic hazard assessment, and using seismic hazard assessment, we can obtain this response spectrum. And this response spectrum provides us the demand corresponding to any period. And in case of buildings, there are multiple periods, but if I consider the first mode, which we also call fundamental mode, so corresponding to that, I can get the demand in terms of base shear. I can calculate. Now, we never design for this base shear, rather we design for a reduced base shear. about 10 times reduced base shear we design here. And then we follow our conventional limit state or working stress method, usually limit state method nowadays. So in limit state method also, we have some partial factors of safety, and we are using characteristic strength in place of the mean strength, which is 95% confidence strength. Actual mean strength will be higher. So due to these three factors, there will be the strength of structure will be higher than what we are designing for. So for example, if we have designed for this V design, actual strength will be given by this light blue curve. So this curve is showing the behavior of the structure, so the capacity of the structure. So we can see that the actual capacity is higher than what we have designed for, but still much less than the actual demand, which is going to come on my structure. And this gap between the actual demand and the actual capacity, which is roughly of the order of 1:5. So 1/5 of the demand is the actual capacity. Taking into account the hidden strength or reserve strength due to factor of safety and characteristic strength, if I count that also, it is roughly 1/5, only 20% of the actual demand which is going to come. So this is going to cause damage in my structure. Problem is that damage is not known, that or we can't exactly estimate that what will be the level of damage. And that's the limitation of current method. And if we ask these questions with the current method, then there is no answer that what is the expected performance of the design structure. I have designed a building following all the procedures of the code, all the do's and don'ts, although those are quite difficult to follow many times. But even if I have followed all those, and the owner asks me that what is going to happen to the building during an earthquake in future, it is difficult question for me to answer, because I do not know that what performance or what level of damage the structure is going to have in a future earthquake. Then the next question is that suppose I want to achieve a better performance. So currently, what the code intends that if it is subjected to a major earthquake, the building will get damaged, but it will be at the verge of collapse. It is not going to collapse. So what we are trying to avoid is the collapse of the structure, because collapse of the building will cause large damage, large loss of life. So we want to avoid large loss of life. But even when the structure is damaged to such an extent that it is at the verge of collapse, so this is severe damage, and there are injuries and some fatalities as well. Only thing is that we are ensuring that the structure is not collapsing. Naturally, this may not be acceptable to many owners if this scenario is explained to them, that what is expected from the building if it is designed as per code. So the next question will be how I can achieve a better performance. So that answer is not given by the current code. Only thing the current code says is that we will use an importance factor, and as we increase the importance factor, the performance goes on improving. But how much improvement? That question is not answered. Now, if a new structural system is evolved, nowadays a lot of changes are going on in the construction industry in India. Many new systems are coming which are not being governed by the code. Current code is either silent or just prohibits those systems. And the reason for that is that such systems, the details for design are not available. And if in some building we want to use any such system, then current code cannot help us. And the whole of the design in the current code is based on this response reduction factor R in case of earthquake. So is there any basis for this R factor? How this R factor has come in the code? So let me tell you the history. So currently the response reduction factor R in the codes have come from past experiences during earthquakes. So whatever structures we have designed in the past, how those have performed during earthquakes, because it is not possible to test full structure under a real earthquake within the lab. It is too large to test. So real test of structures, buildings takes place during real earthquakes. So one of the jobs which we have is that whenever there is an earthquake, we visit the damaged structures and try to understand how different structures have behaved and whether the response reduction factor used for those structures was adequate or not. So it is based on that limited experience, and that's why it is not fully rational. So recently, with performance-based design methodology, a rational method of obtaining a realistic value of R has also evolved. And using nonlinear analysis, we can estimate for that specific structure what is the most reliable, most optimal value of R. So these questions can be answered using this methodology, which we call performance-based seismic design, PBSD. And in performance-based seismic design, we can target a performance and we can target a hazard. So two parameters we have to decide. One is the hazard level, that how strong earthquake we are going to design for. And then under that earthquake, what level of damage we are going to accept. So one is the hazard level and another is the damage level or the performance level. And the objective of the design is expressed in terms of these two parameters, that this performance under this level of hazard. So I will explain both to you, how we quantify the different levels of hazard and how we quantify the damage level. Because defining the damage in descriptive terms is easier, but design cannot be done in descriptive terms. We need to define it in terms of some engineering demand parameter. So that engineering parameter, which we are using to define the damage, that's a little more complex. And we have to understand, I will give the guidelines, whatever guidelines are available in literature, I will share you with those also. And using those guidelines, we can decide that what engineering parameter we can allow if I am targeting a particular level of damage or particular performance level. So this procedure we can simply understand like this, that we try to obtain the value of response reduction factor R in such a way that it results in the targeted damage in my structure. That targeted damage may be no damage at all, or that targeted damage may be so high that it is just, the structure is just at the verge of collapse or in between. So I can decide any targeted damage level in between these two extremes, no damage to collapse. And then I can determine the value of response reduction factor in such a way that when I'm designing my structure with that force, I'm able to achieve that targeted damage level. So here also, the demand is given by response spectrum, especially when we are using pushover analysis. So I told that pushover analysis is the simplest method. That's why it is attractive. But another charm is that pushover analysis can be used with response spectrum. And obtaining design response spectrum is much easier than obtaining design time histories. So currently the guidelines in the codes are not available how to get the design time history, especially in our code. So getting time histories corresponding to the demand level at my site is more complex. Getting the response spectrum is easier. I can get it directly from the code or through site-specific hazard analysis. So this demand is expressed in terms of response spectrum, and capacity of the structure is expressed in terms of its load displacement behavior. So initially the structure is elastic, then it yields, and then it plastifies, and it becomes almost flat, and then finally it collapses. And then we reduce this demand by a factor in such a way that I can get the damage corresponding to that targeted performance level which I have decided. So this procedure is called performance-based design, and pushover method is the method to obtain this capacity of the structure in terms of this load displacement behavior. So how to obtain this full load displacement behavior, that is actually our objective today. So as I said, that in performance-based design, we are having a performance objective, and that objective consists of two labels. One is the performance level and another is hazard. So we express a particular performance level corresponding to a particular hazard. And we can have multiple performance objectives also. I will explain that. And in contrast, the conventional design which we are following nowadays, currently, that is, we are defining certain limits on the member forces. So we calculate the demand on the member forces, and that demand is reduced demand. And then we design our members in such a way that that demand is satisfied. And here we are not trying to estimate what will be the performance, how really the building is going to perform. That's the limitation. So these performance objectives, these are of two types. One is the structural performance level and another is the non-structural performance level. So structural performance level is related with those components which are supporting the gravity and lateral load of the structure. So those members which participate in resisting vertical load, that is gravity load, and the lateral load, wind and earthquake, those are our structural systems or structural components. But in addition to that, we have a number of non-structural components also. So we have to define the performance objective in terms of structural performance as well as non-structural performance. For example, when we are designing a hospital, merely a building which is not damaged, which is withstanding earthquake, is not enough. The hospital should be functional, and a functional hospital will require functioning of all the services. So whatever oxygen lines are there, water supply are there, vacuum lines are there, sewage, that's very important. That should also be functional. So all those are also to be taken care of, and power supply, because in the city there may not, after a major earthquake, there may not be power supply in the city. So we have to make arrangement for power supply, standby power supply, so that even if the power supply from the city grid is not there, the hospital should remain functional. And these performance levels we define in terms of three engineering demand parameters. The first engineering demand parameter which we use is inelastic member deformation. So till the member is elastic, there is no damage. And the damage starts once the member yields. It goes into inelastic range. So how much it goes into inelastic range, that will define the extent of damage. So we will define the damage in any member in terms of inelastic member deformations. Then another way, which is simpler, because getting the inelastic member deformations and the limits corresponding to different performance levels is a bit complex. A more simpler approach is interstory drift. And interstory drift also controls the performance of non-structural components. For example, partitions, services which are connecting adjacent stories, the top floor to bottom floor, all their damage is governed by the interstory drift. So interstory drift is also an important parameter. And in some cases, floor acceleration. So when we have any equipment mounted on the floor, then the anchorage and performance of that equipment will depend upon the floor acceleration. So the ground motion gets amplified when it is moving from ground towards the roof of the structure. And on each floor level, there is an amplified ground motion. That amplified ground motion should be controlled in such a way that the equipment which I need after an earthquake, those equipment should remain functional, and their anchorage to the floor should also be intact. Because if the equipment is sliding or tilting or overturning, then also the performance or the operation of hospital or any such building will not be there. Now, two documents which we will be using in this talk also, and which you require. This is AC 41. Earlier, AC 41 itself, up to AC 41 2017, the modeling criteria was given in ASC 41 document itself. But in the latest revision, ASC 41 2023, the modeling criteria has been taken from ASC 41 and put in this ACI 369.1 document. So now we have to use these two documents together. If you are referring to an old version of ASC 41, you can find guidelines for modeling there itself. But in the recent document, you have to read ASC 41 along with ACI 369.1 2022. So these two documents together we will be using. And then there are two documents available on nonlinear modeling. One is a SPEAR 72.1 document, and this is NEHRP design brief. So a guide is there. So these two documents will provide you the background, the theoretical background of nonlinear analysis. So as I said, that we have to define a hazard level and a performance level. Hazard level is defined in terms of return period. Earthquake is a rare phenomenon, and like all other phenomena, natural phenomena like flood, this is also having a random nature. So like we define a return period in case of a flood, in the similar manner, we define a return period in case of earthquake. And larger earthquakes have longer return period, or those have lower probability of occurrence. So we also define the hazard level in terms of probability of occurrence in 50 years, because 50 years usually we consider the life, design life of a structure. So what is the probability of occurrence in 50 years? So 50% probability in 50 years, it has a return period of roughly 75 years and 72 years to be more precise. This earthquake we call serviceability earthquake. So you can see this 50% in 50 years, it is representing an earthquake which has even chances in the lifespan of the structure. So our structure should be ready to resist these level of earthquakes without any effect. That means the structure should be serviceable under such an earthquake. So that's why this is also called serviceability level earthquake. So an earthquake having a return period of 75 years, the structure should have no damage at all, neither structural nor non-structural, and the structure should remain serviceable. Then another important level of hazard is this 10% in 50 years, which is having a return period of 475 years, and roughly we say 500 years. This we call design basis earthquake. So design basis earthquake is the earthquake for which we are designing our structures currently in the code. So when we are designing our structures currently in the code, we are designing for DBE, and corresponding to DBE, we are using a response reduction factor, which is 5 for spatial moment resisting frames. In case of properly detailed RCC buildings, this response reduction factor is 5. So first we estimate the earthquake or response spectrum corresponding to DBE, which is having a return period of 500 years, and then we divide it by 5, and then that we consider in our design. But the earthquake against which we do not want collapse is the maximum considered earthquake. This is sort of an upper limit. So theoretically, there cannot be an upper limit to a random phenomena like earthquake. Earthquakes even more severe than this are probable, but their probability is very low, less than 2% in 50 years. So for practical purposes, we consider this 2% in 50 years as the largest earthquake which can affect our structure. And we want that under this 2% in 50 years or 2,500 years return period earthquake, our structure should not collapse. So it is interesting. We are designing for DB, and we are having intention that it should not collapse under MC. So this also we have to understand. And here from DB to MC, we are taking advantage of hidden strength of the design which we are having in our design. So because we are using limit state method with some partial factors of safety. We are using characteristic strength. So actual strength will be roughly 2 times. So we even utilize that hidden strength, the factor of safety which we are having, that also we use in case of earthquake. And taking advantage of that, we design it for DB and expect that under MC, which is roughly 2 times of DB, so under that, our structure will not collapse in the conventional method. When we will be using performance-based method, then for each of these levels, we can estimate the expected performance explicitly. And then we can decide whether that expected performance is acceptable to us as owner of the building or as occupant of the building, if that is acceptable to us or not. And if it is not acceptable, we can go for a better performance objective. So as I said, that performance levels, on the other hand, are defined in terms of structural performance and non-structural performance. Structural performance, SP, structural, or rather performance of structural components. So this is immediate occupancy, SP1, SP3 life safety, and SP5 collapse prevention. And in between, these are ranges. So SP2 is actually a range, SP4 is also a range. So 3 labels commonly we consider, especially in ASC 41, immediate occupancy, life safety, and collapse prevention. Immediate occupancy, you can understand that the damage is practically not there. So here also we allow the structure to yield and undergo some inelastic deformation, but that inelastic deformation is limited to such an extent that practically there is no damage, and the structure can be occupied immediately after the earthquake. And in case of life safety, we accept some damage. So when the structure is getting damaged, the chunks of concrete and masonry will be falling, but we have to ensure that large chunks of concrete and masonry should not fall. And because if these large chunks are falling, there can be life-threatening injuries. So some injuries may be there, but life-threatening injuries should not be there. So we try to save the life. There should not be any risk of life loss corresponding to this performance. And then the last one is the collapse prevention. This is the minimum performance which we want in any case, because collapse we cannot afford. Collapse will cause large scale loss of life, and that we want to avoid. So in collapse prevention, it is understood that some fatalities are expected. What we don't want is that the building is not collapsing. And currently our code, although it doesn't say anything, it doesn't guarantee, it doesn't ensure, but it is understood that the code will be able to provide us this. But it is just mere understanding. There is no framework to ensure that. Then non-structural performance, similarly we define by the NP, and NPA corresponds to operational. So structural performance is defined by numerals 1, 2, 3, 4, 5, 6. The non-structural performance is defined by alphabets A, B, C, D. So operational means there should not be any damage to non-structural components which can affect functioning of the building. So minimal damage or no damage. Then NPB, position retention. So here the damage, cracking may occur in the non-structural components. Those may not remain functional because after cracking there may be leakage. It may not be operational, but it should not fall down because non-structural components are the first to fall down. For example, a heavy pipe which is running on the ceiling and that falls down, it can cause injury. So position retention means that there will be no injury. The system may not be functional, but it should not cause any injury. Then NPC is the life safety. Here, some smaller equipment may fall, but the larger equipment, larger services, larger non-structural components should not fall, because if larger structural systems are larger non-structural components are falling, those can cause life-threatening injuries. So that type of injuries are to be avoided. So that is C. And of course, in conventional design today, we do not consider the non-structural performance at all. So this is also possible, that we focus only on the structural performance. We do not focus on non-structural performance. For example, in case of ordinary residential buildings, we are not worried too much about the operational status of the building after the earthquake. We are more worried about prevention of collapse and safety of life. So with the help of these two parameters, one is the hazard or hazard level and the performance level, we can define the performance objective. For example, if we are designing a hospital building, we will like that the hospital should remain operational at least under DB, design basis earthquake, 500 years earthquake. And if very severe earthquake, 2500 years return period earthquake is there, at least life safety should be. On the other hand, if I'm designing a normal building, maybe under DB, I will say that it should be life safety, and under MC, I will say that it should have collapse prevention. It may not sound very comfortable as an owner if I say that I'm targeting only collapse prevention, I'm not targeting life safety, but economically, maybe we have to take a decision that I'm not targeting life safety, I'm targeting collapse prevention. So those decisions are not easy. Those are not purely technical decisions. Those involve economics also. So together with the owner, we have to take these decisions. Now, recently, our code is being revised. Many of you might have seen this revised code also. And the current code, which is dividing the country into 4 zones, zone 2, 3, 4, and 5. So it starts from zone 2 up to zone 5. 4 zones are there. You are familiar with that. And that is based on deterministic seismic hazard assessment. In deterministic seismic hazard assessment, we do not get any return period. That's why the current code does not talk about DB or MC or return period, or whether it is 475-year return period or 2,500 years return period. Those terms are not there in the current code. Whereas in the revised code, the zonation has been changed. Now there will be 5 zones, starting from zone 2 to zone 6. So there are 5 zones. And you can see that zonation map has also changed. So whole of this Himalayan region, Himalayan belt, this has gone into zone 6. And the foothills and the plains in the adjacent to Himalayas, that has gone into zone 5. And Delhi, of course, remains in zone 4, and perhaps there is no change in Bombay also, that zone number remains same. But the hazard now is also defined along with return period. So the zone factor earlier, I mean in the current code, the zone factor is fixed for one zone, 0.36 for zone 5, 0.24 for zone 4, and so on. But here, different zone factors along with the return periods are defined. So the MC, which we discussed, corresponding to 2,500 or 2,475 years return period, those zone factors are defined like this. In zone 6, it is 0.75. In zone 2, it is 0.15. So 0.15 to 0.75, it is varying. Now, one curiosity you may be having, that how this zone factor, which is given in the revised code or the draft code, which is yet to be published, these zone factors, how these are comparing with our current zone factor. So current zone factor is based upon DSHA, deterministic seismic hazard assessment. And if we have to compare with the probabilistic seismic hazard assessment, then this is the approximate relationship. So the zone factor Z, which is given in our code, is median effective peak ground acceleration or zero period acceleration, which we call. It is the value in the response spectrum corresponding to zero period, t equal to 0. So that value, because we multiply by Z, and to get the responsive spectrum, our code gives a spectral shape, normalized spectral shape, where the value corresponding to t equal to 0 is 1. So that needs to be multiplied by this zone factor Z. And this is median value obtained from DSHA. Now, if we multiply it by 1.5, so 1.5 Z, that becomes 84 percentile. that is close to 84 percentile, which we are obtaining from DSHA, and it is close to MC level hazard. So in probabilistic seismic hazard assessment, MC, which means 2500 years or 2475 years return period earthquake. So this 1.5 JAD will be corresponding to MC. And DBE, I told you, that is roughly half. So 1.5 into JAD by 2, that represents the DBE. And this DBE we use for design using limit state method or ultimate limit state. In case of bridges, we are using ultimate limit state method or so-called strength design. So we are using 1.5 into JAD by 2 in our analysis. You may be familiar with JAD by 2. JAD by 2 is appearing in calculation of AH. So AH is JAD by 2 into I by R into SA by G. And 1.5 is appearing as a load factor. So there is a confusion in the current code. Because it is giving a load factor, many of our designers think that we are increasing the load by this factor. Actually, we are not increasing. We are using that load factor of 1.5 to convert the median value of JAD given in our code corresponding to MC. So this 1.5 comes from here by 2 to convert into DBE. And if I use only JAD by 2, then it corresponds to serviceability earthquake. Serviceability earthquake is used along with working stress or for checking serviceability limit state. So if we are using JAD by 2 alone with factor 1, then we will be using it with working stress method. If I'm using 1.5 JAD by 2, then I will be using it with limit state method. So we can compare the response spectra for different return periods with our current code. So this value here, currently this value is given 1. And this is the value I was talking about, JAD-P or effective PGA. So the response spectra are normalized with this value. That's why this value becomes 1. And actually, our code, which currently writes this as SA by G, it is incorrect. It should not be SA by G. It is actually SA by JAD. Because when I divide this by JAD, then only this value is 1. And if I want to get the response spectrum corresponding to MC, I have to multiply this by 1.5 into JAD. So the shape of the response spectrum, which is given in the code, actually it is shape. It is not response spectrum. It is shape only. When I multiply this by JAD or 1.5 JAD or 1.5 JAD by 2, then it will become a response spectrum. If I multiply it by 1.5 JAD, it becomes response spectrum corresponding to MC. If I multiply this by 1.5 JAD by 2, that is 0.75 JAD, then it becomes a DBE. And when I multiply it by JAD by 2, that is 0.5 JAD, then it becomes serviceability earthquake. In terms of return period, this is 2475 years return period. This is 475 years return period. And this is 75 years return period. So if we go back and compare it with the new code, so this 2475 years, this 0.75 in zone 6, actually it should be compared with 0.36 into 1.5. So in previous or current code, it's still not previous. The current code is still, it is 2016, which is in force. So the maximum zone factor is 0.36 for zone 5. That needs to be multiplied by 1.5 to convert this into corresponding to 2475 years. So in place of 0.54, I am having 0.75 as the maximum. But in zone 2, current factor, zone factor is 0.1. And I multiply by 1.5, so that remains 0.15 only. So there is no change in zone 2. Zone 5 is close to current zone 5. So 0.54, we can say is our current zone 5. So in the new zone 5, it is 0.6, slightly higher. But zone 6 is much higher. Compared to 0.54, it becomes now 0.7. So we will be needing these response spectra corresponding to DBE, MC, and serviceability earthquake in our pushover analysis also. That's why this background was necessary. So with this background of the response spectrum, let's move now to the nonlinear or inelastic behavior of structures. So what do we understand by inelastic behavior of a structure. Let's take an example of a simplest structure, that is a cantilever. It is subjected to a vertical load P here. So under this load P, it will deflect. Let us say this deflection is delta 1, and I can plot the load versus displacement curve like this. So under load P, I am getting this delta 1, and this behavior can be represented by a straight line. We know currently our stiffness, which is P over delta, that is constant, or the relationship is P is equal to K delta, that is relationship of a line. So this we call linear behavior. So this relationship between P and delta is linear. If I increase P further, the displacement will increase linearly and it will continue. So with our current analysis method, if we continue the analysis, the displacement will continue up to infinity. So I can go on increasing P, the displacement will go on increasing, and the displacement can go infinity. But that's not the real behavior, we understand. So this is the limitation of linear behavior, that we keep the proportionality of displacement and force till infinity. And suppose I start unloading the structure, then it will follow the same path. And if I apply the load in the opposite direction, then it will continue like this up to minus infinity in the other direction. So the relationship is linear. That's why we call this method or this behavior as linear. And it is following the same path in loading and unloading and coming back to the origin when P is equal to 0. So there is no permanent displacement. This we call elastic behavior. And in elastic behavior, whatever work I do while loading the structure, so the work is the area below the load displacement curve. So whatever work I do in deforming the structure, the same energy I get back when I am unloading the structure. So there is no loss of any energy, or we do not have any energy dissipation. So loading and unloading follows the same path, and the path is linear. That's why this behavior we call linear elastic. But this is simplified, assumed behavior, which we have assumed to simplify our analysis. And whatever analysis we have learned in our college, that follows this. Now, real behavior is different. In reality, what will happen? When I will apply this force P, only initially it will be linear. And as I increase the load, it will follow a nonlinear behavior. So the load displacement behavior is nonlinear. This is the real behavior. In case of normal loads, that is gravity load, dead load, live load, and wind load, we limit the force within this range. So analyzing the structure, assuming it to be linear elastic is all right. But in case of earthquake, actual load is much more than even the capacity. So the structure is bound to go into inelastic and nonlinear behavior. So this is nonlinearity because the relationship between P and delta does not remain linear. And if I do unloading now, it will not follow the same path. It will follow this path. And you can see that the area below the two curve, the loading curve and the unloading curve is not same. The area under unloading curve is less than the area under the loading curve. So I have done more work while loading it, and I have got less energy while unloading it. So some of the energy has been dissipated, and that energy is equal to the area which is bound by these loading and unloading curve. So this much energy has been dissipated. And another thing you see, that when I unload the structure fully, that means that I remove the load fully. The load is 0 here. It does not come back to the original position. The displacement is there. So here is a permanent displacement. I have removed the load fully, still it is permanently sagged. So it has not gone back to the original position. And if I want to bring it to the original position, I have to apply the load further in the opposite direction, in the upward direction, then it will go back to the 0 displacement position. So at 0 displacement position, I have to apply P in the negative direction, opposite direction. And if I continue this, In the other direction, I will get the behavior, nonlinear behavior again. And if I unload it from here, I will get a hysteresis, a loop. And the advantage of this hysteretic loop is that it is dissipating the energy. Whatever work is being done while loading the structure, we do not get back the same energy while unloading. So part of the energy which is imparted to the structure has been dissipated. Dissipated means that energy is not destroyed because of the conservation of the energy. It gets converted into other forms of energy, mostly the heat. So that energy gets converted into heat, and the vibration of the structure or the deformation of the structure is reduced. So in case of earthquake, this is very much advantageous because we can visualize earthquake as through its shaking, it is providing some energy to the structure. It is imparting some energy to the structure, and the structure has to dissipate the energy. The structure can dissipate energy through these systems. So nonlinear behavior of materials or members depends upon the nonlinear behavior of materials. So here the behavior of concrete is shown. So we see the stress strain curve. So this lower one is the stress strain curve of unconfined concrete. So in case of unconfined concrete, the peak occurs at a strain of roughly 0.002 and the failure occurs at a strain of 0.005. In our code, we consider it to be flat here up to 0.0035. So in place of this behavior, we consider an idealized behavior like this. But what you see here is that the ratio of ultimate strain to the peak strain is less than 2 or equal to 2. 0.0035 divided by 0.002. So there is very small inelastic range of strain in case of unconfined concrete. But when we confine the concrete, I'm not going into that detail that how unconfined and confined concrete behave, but you can see this in any book. When we confine the concrete, its strength increases and its ductility. That means the inelastic range of the material, strain range in which the structure or the material behaves inelastically, concrete behaves inelastically, that range, strain range increases tremendously. So you can see that confined concrete stress strain behavior is like this. Unconfined concrete, it is a very brittle. Confined concrete becomes somewhat ductile, but still not as ductile as the steel because this ultimate strain is of the order of 0.02, 2%. Whereas in case of steel, it is of the order of 20% ultimate strain. So I will show you the behavior of different types of reinforcing steel. So mild steel, which we are not using anymore. So this bottommost curve is for mild steel. The yield strength is 250, roughly 250 megapascal. And we have a yield plateau. Then there is a strain hardening, and the ultimate strain is more than 25%. You can see here. So this is in percent, more than 0.25. More than 25%. So that is 0.25. And in case of concrete, even after confinement, we were able to get 0.02. So that is 2%. So much less than what we are getting here. Now, strength of steel can be enhanced using different techniques which require change in chemical composition, then cold working or thermomechanical treatment, the TMT. Nowadays, you are hearing about Fe500 and Fe550. So these are the steels, Fe500 and Fe550. And what Fe415? Okay. So you can see that the strength can increase here, but the ductility reduces. So ductility here is roughly 14%. And our code IS 13920 says that any steel which is having total elongation less than 14.5% cannot be used. So minimum 14.5% ductility or ultimate strain in the structure in the steel we should have to use it in the seismic area. Then only we can achieve ductility in the member. So from the material, we will move to section. Let us say a section of a cantilever beam. Section can be any general shape. So I have taken a general shape here. In fact, this I have taken from book by Priestley. So any general shape can be there. And you know how to analyze a section in your BTech first year or second year. You have learned analysis of beam sections. And what we do, we assume a strain profile. One of the assumption is that the plane sections after bending remain plane and normal to the neutral axis. So the strain is given, strain variation is given by a straight line. A linear variation is there. And then the maximum strain in concrete, we allow up to 0.0035 if it is unconfined. If it is confined, we can go higher strain, also depending on the stress strain curve of the confined concrete. And then we assume a level of neutral axis and then plot the stress strain curve of concrete and steel. So corresponding to these levels of strain in concrete, we get the stresses from the stress strain curve of concrete. The stress strain curve of concrete is plotted here continuously because above neutral axis, concrete is uncracked. Below neutral axis, up to certain depth, the concrete is uncracked. Beyond that, the concrete is cracked. So this is the tensile limit on the concrete strength, the tensile strength of the concrete, Ft. So up to that, it will be continuous. We generally do not take this into account. This is quite small. So we ignore this. So compressive force we calculate from the area of this stress diagram, and tensile force we get from the steel. So the stress we estimate corresponding to this level of strain and then multiply it by the corresponding area of the steel bars. So we get C and T. We satisfy equilibrium, C equal to T, and that gives us the depth of the neutral axis. Once we get the depth of the neutral axis, we can calculate the moment about the centroidal axis of the member, and that will give the moment capacity at that strain level and the angle of this strain diagram. This is interesting. This is curvature. So this angle is equal to the curvature. So you might have earlier heard about curvature. So curvature is nothing but rate of change of slope or second derivative of vertical deflection. So d square y by dx square, that is the curvature. It can be shown geometrically that d square y by dx square, that is also equal to this angle of the strain diagram. So this is the curvature. So by this method, we can calculate moment and curvature corresponding to different strain in concrete and steel. So by following different levels of strain in concrete and steel, we can calculate the values of moment and curvature, and we can plot a moment curvature diagram. So this is the first important parameter which is used in nonlinear analysis, that is moment curvature diagram of a section. So stress strain curve, that was the property of the material. Moment curvature diagram, this is the property of the section. Still, member has not come into picture. It is just the section. And this gives us a very important parameter which we use in our analysis as stiffness. So cracked section stiffness we get from moment curvature diagram. So when we go on increasing the strain in concrete, somewhere here the concrete is cracking in tension. So the strain in concrete reaches the cracking strain. So this is the point. Then here you see the stiffness changes. The stiffness is slope of moment curvature diagram. So slope of moment curvature diagram is equal to EI. You are familiar with the relationship M upon I is equal to F upon Y is equal to E over R. So 1 upon R is also equal to curvature. So slope of this moment curvature diagram gives us the value of EI. So this is the point where the concrete is cracking, and somewhere here is the point where our steel bar, the first steel bar is yielding. So after that, this becomes, if you see the curve becomes nonlinear. Till this point, it is more or less linear. After the yielding of first steel bar occurs, and we know steel bar we design our structures in such a way that the steel has to yield before crushing of the concrete. So before the strain in concrete reaches 0.0035, the steel has to yield. So steel we design under reinforced structures in RCC, and here the yielding of steel occurs first, and due to that the moment curvature diagram becomes nonlinear. So if we join the origin with this point and draw a line, this we treat as the effective cracked section stiffness of the structure. So in the code, you might have seen the stiffness modifiers for different components. Those stiffness modifiers can be obtained from here. So basically, it is the slope of this line which is joining the first yield of a steel bar with the origin, and the slope of this line. And slope of this line is giving us the secant stiffness. So it is the secant stiffness, or rather secant rigidity, EI we call as rigidity. Length is still not involved. Here we are still considering the section only. And then when either the concrete gets crushed or steel bar reaches its rupture, that gives us the ultimate value of curvature. So this is the ultimate value of curvature phi u. And when we join this with the first yield and extend this curve, and we replace the original curve by a simplified curve which consists of two lines. So we also call it equivalent bilinear idealization. So equivalent bilinear idealization consists of two lines, one initial inclined line and another this line which is almost flat. So depending on the type of the section or reinforcement detailing of the section, this line may be having a slight positive slope, it may be perfectly flat, or it may have sometimes even the negative slope. So this behavior is called, when it is perfectly flat, we call it plastic, or ideally plastic. This is strain hardening, and then there can be strain softening as well when it is sloping downward or there is a negative slope. And ratio of this phi u to phi y, this is important. This we call curvature ductility, mu phi, that is phi u over phi. Now from section we move to the structure. The simplest structure is a cantilever. A pier of a bridge we can consider as a cantilever, and the force is acting at the CG of the superstructure, and the moment diagram is linear here. And we know moment and curvature are related with m upon ei. So the curvature diagram will also be linear. But when we go on increasing the force here, the moment increases. This moment curvature, this curvature diagram becomes nonlinear. And the displacement at the top we can obtain from double integration of this curvature diagram. We know that curvature is second derivative of displacement. So displacement we can get by double integration of curvature. We can also obtain this geometrically using moment area theorem. So we take the area of the moment diagram or area of the curvature diagram and then take its moment about this point, that will give us this displacement. But that is valid only till the moment curvature diagram is linear. Actually, our moment curvature diagram becomes nonlinear, and we replace it by equivalent bilinear curve. So this is our equivalent bilinear curve, and we consider this equivalent bilinear moment curvature curve as consisting of two diagrams. One is this linear variation of curvature. So here we can see that the curvature is varying linearly up to yield, and whatever is the curvature beyond yield, that we lump in the form of this rectangular diagram at the base of this cantilever. So we call this as the notional plastic hinge. So in reality, what is happening? Wherever the curvature is exceeding phi y, yield curvature, the yielding of steel is taking place. So steel is yielding roughly at this height. So steel is yielding in whole of this height. But we represent it by equivalent triangle and rectangle. And the height of rectangle is taken in such a way that the displacement which we will get at the top, that is same. That comes out to be same as we are getting from experiment. So this LP, the plastic hinge length, this is obtained empirically from experiment by adjusting this length in such a way that the displacement which we are calculating from moment curvature diagram at the top and what we are getting from the experiment, that matches. So this length is a smaller length here. It is not the length, sometimes people get confused that this is the length in which steel is yielding. So plastic hinge length is not the length of yielding. Yielding occurs in much longer length. Plastic hinge length is just a notional length which is calculated in such a way that if I consider the plastic deformation to be lumped in this length only, then I will get the same displacement as obtained from experiment. So some little geometry is done, and with that we can calculate the displacement at the top using moment area theorem or by double integration. And this plastic hinge length, as I said, this comes from empirical relationships by comparing the theoretically calculated displacement with the practically obtained displacement, and LP is obtained in this form, K into LC plus LSP. This is the length of strain penetration, and strain penetration is this length. Because what happens when this beam is bending, the maximum moment will occur at the base, and there the strain or stress in the steel will be maximum, equal to the yield stress. And then this stress will not suddenly become zero because the steel is anchored into the foundation. So it will not suddenly become zero. The plastic strain will continue to some level or some distance inside the support, or if it is a beam column joint, then into the connecting member. This is called strain penetration. So length of strain penetration is this much, that is LSP, and LP is at least 2 times this LSP. And LSP again is given empirically in terms of the yield strength and the diameter of the longitudinal bar. So this DBL is the diameter of the longitudinal bar. And then K factor is obtained like this. This is the ratio of ultimate stress or ultimate strength of the steel to the yield strength, Fu by Fy. Because larger the strain hardening in the steel, longer length of the steel will yield and longer plastic hinge length we are going to get. And longer is the plastic hinge or larger is the plastic hinge length, more ductility, more energy dissipation we are going to get. So that's why this ratio Fu by Fy is important. And if you look at IS 13920, IS 13920 also fixes a minimum value of this. I do not remember whether that is 1.15 or 1.2. So a minimum value of Fu over Fy is given in our code. And that is to ensure that the plastic hinge length should be sufficient, because this length will decide how much energy we are going to dissipate. Then we can convert curvature by double integrating it at every point or using moment area theorem. We can convert this into displacement, and from moment curvature I can get the force displacement curve. So corresponding to yield curvature I will get yield displacement, corresponding to ultimate curvature I will get ultimate displacement, and ratio of delta U to delta Y, that becomes the displacement ductility, mu delta. Mu delta is delta U by delta Y. So by section analysis I can get, using the same principle which we have done in beam analysis, RCC beam theory, using the same concept, we can generate the nonlinear force versus displacement curve. And here I will simplify this into bilinear curve. So initial portion is given by a straight line, inclined straight line, slope of which is giving the stiffness or effective stiffness or cracked section stiffness of RCC. In case of RCC, cracking of section causes reduction in the stiffness. So this is representing the cracked section stiffness of the structure. And here the yielding occurs. Now this point is also notional. You can see that Actual curve is not passing through this point. So this point we are calling the yield point. Actually, this point is lying at the junction of these two lines, which I have used to represent or to make a simplified representation of the actual load displacement curve. So I represent it by these simplified curve, two lines, so that the calculation becomes easier. So later on, when we will be doing calculations for inelastic structures, nonlinear structures, then we will need this shape. And this will be, if I use equivalent bilinear curve, then the calculation will become easier. But we do it in such a way that the area under the two curves, the equivalent bilinear curve and the actual load displacement curve, the area remains same. And why that is important? Because we have to balance the energy dissipated. So energy which is imparted during earthquake, the structure has to dissipate. And the dissipation capacity will depend upon the area under the load displacement curve. That's why this equating the area below the two load displacement curves is important. We can do some simplifications or some use some geometry, and we can calculate curvature like this: epsilon c by c. C is the depth of the neutral axis, or epsilon s. D minus c becomes the depth of the neutral axis from steel. And I can also write down this as epsilon c plus epsilon s by d. So like that, and ultimate displacement I can calculate. So I will share this slide with all of you, or rather all the slides with all of you, and you can look in this mathematical derivation. It is simple, but it requires some geometry. Now, so far we have considered a very simple structure, that is bridge pier, and which is a cantilever. That is the simplest structure. Other structures are not so simple. So next, more complex structure is a column, which is fixed at top and fixed at base. So we can treat this curvature, this column, which will be deforming under lateral load in double curvature, as consisting of two cantilevers. So this has one cantilever and this has another cantilever. And here, this rotation, which is joining the two ends, so this we call chord. So chord is a line joining the two ends of the deformed shape of the column, and this angle with the tangent at any one end, this angle theta, this is important. This we are calling chord rotation. So in case of nonlinear analysis, we are talking about chord rotation. Actual rotation, which is del u by del x or del y by del x, where y or u is the displacement. So the slope, you can see that that is varying. It is not constant. But this chord rotation, you can see that it is unique for one member. And that's why we are using this chord rotation in nonlinear analysis, not the actual slope, because actual slope will vary from one point to other. And actually, it is representing the displacement, the total drift. It is actually the ratio, drift ratio. So total displacement of one end with respect to the other end divided by the length of the member. So this rotation is used in SC41 to define the performance of the structure. And this cantilever, this double curvature column, we can represent as two columns having one hinge at the base of this cantilever and another hinge at the base of this cantilever. And you can see chord rotation of this cantilever, it's same as the chord rotation of this double curvature bending column. So this is the definition of chord rotation given in SC41, and it is to be understood that the theta rotation given in SC41 or ACI is actually chord rotation, not the conventional rotation which you think of. Now, so far we have discussed the behavior under monotonically increasing load. So the load P, which we were applying on the cantilever, that goes on increasing in one direction. But in case of earthquake, the force is reversible. Earthquake is reversing its direction in a fraction of a second. and it is any member is subjected to reversible loading. So it is subjected to reversible or cyclic loading like this. So under cyclic loading, initially, let's say our member is linear elastic, then it yields, it becomes nonlinear, and when I unload, it follows this path. This path is approximately parallel to this. And this is the permanent displacement. And when I apply the load in the other direction, it moves like this. And under cyclic load, I will get this type of hysteretic behavior. Now, this behavior we call almost ideal behavior. Almost ideal behavior is that the slope of the loading and unloading curve, or the stiffness in the loading and unloading, is same. Although you can see here some reduction is taking place. This slope is higher and this slope is slightly lesser than this slope. So slight reduction is there in case of steel. So in case of steel, properly detailed steel structure, the behavior is almost ideal. But let's go for RCC, which we are discussing today. So you can see that initially the slope is quite high. So this is the slope of the initial load displacement curve. And in successive cycles, it goes on reducing. You can see that the slope is reducing. So the stiffness degrades in cyclic loading. So under cyclic loading, stiffness of RCC structure does not remain same as we have obtained using moment curvature relationship, or by multiplying EI with the so-called stiffness modifier. So that stiffness does not remain same. That is one problem. Another problem is that at the same displacement under different cycles, the strength goes on reducing. So you can see in the first cycle here, the strength is this much. Next cycle, it is this much. Next cycle, it is this much. Next cycle, it is further down, further down. So even at the same displacement, the strength goes on reducing. This is called cyclic degradation of strength and stiffness. So under cyclic load, the stiffness also reduces in successive cycles. The strength also reduces in successive cycles. And then the shape of the curve, if you see here, this load displacement curve here, the area is reducing. This is called pinching. So due to pinching, if you compare it with this curve here, you can see that the area here is much larger. And the energy dissipated by this structure per cycle is equal to the area of that cycle. So if I take the hysteretic curve in one cycle, area under that cycle, or area of the hysteretic loop in that cycle, is representing the energy dissipated in that cycle. So we can see in case of RCC structures, due to this pinching, the area of the hysteretic loop is reducing and the energy dissipated per cycle is reducing. So under the same displacement, it will be able to dissipate less energy. So these two effects are in addition to what we are getting from monotonic load displacement curve. So in monotonic load displacement curve, these effects are not there. But monotonic load displacement curve, I can get very easily using the analysis, which we have done already in case of RCC beam design. In case of masonry, it is even more pronounced. I will not go into the detail. So what we have to do, we cannot take the monotonic load displacement curve as it is. We have to take into account the cyclic effect also, because earthquake causes cyclic loading. So for that, we have to take an envelope of the cyclic load test. So under cyclic load test, this is the hysteretic behavior. And if I draw an envelope, this envelope is called backbone curve. So this is backbone curve of a member. And this backbone curve initially, up till, let's say, slightly ahead of yield point, it is same as the monotonic curve. So in this range, it is same, but beyond that, it reduces. Failure occurs at much lesser displacement than delta U, which we have obtained from monotonic curve. So I can calculate the initial stiffness and the yield strength using monotonic analysis, but I cannot calculate the plastic strength or the plastic deformation capacity using monotonic load. So this we have to keep in mind. Using section analysis, you can calculate only strength, yield strength, and the initial strength. So from where we will get the rest of the curve? The rest of the curve comes from the experimental test. And this backbone curve has been idealized in SC41 like this. So actually this A to B, this is the initial line. In equivalent bilinear curve, you saw that this is initial stiffness ratio, slope of this line is showing the initial stiffness. So this you can get from section analysis. The yield strength also you can get from section analysis. So this much portion you can get from analysis. B to C, and then at C, the concrete gets crushed. And when concrete gets crushed, concrete reaches its ultimate strain. In case of unconfined concrete, that is 0.0035, but actually the concrete is confined. So this strain, the strain at this level is of the order of 0.02 if it is properly confined. So it will depend upon the confinement. So if it is properly confined, then when the concrete gets crushed here, then the strength is suddenly reduced. So you can see that there is a sudden drop from C to D. And then the member starts resisting the force through catenary action, and then finally steel ruptures here. So point E is the failure. Here the failure or collapse of the member takes place. This is called capping strength at point C. And before that, it is called pre-capping behavior, and this is the post-capping behavior. So up till point B and slightly ahead of point B, let us say up to here, we can obtain using monotonic curve. But beyond that, it is to be obtained experimentally. It cannot be done using monotonic curve or section analysis. So this curve, idealized curve, two types of curves are given. One is this curve, and another is a trilinear curve. That was bilinear curve. This is the trilinear curve. For some of the members, the code proposes trilinear curve. So here, let us say in case of infill, initially the infill is uncracked. So the stiffness is higher. When the infill cracks, we get a lower slope, lower stiffness, and then it yields. And finally, it loses its strength when the cracking is significant, and finally it collapses. So these two types of curves, backbone curves, are used in SC41 and the corresponding parameters. So these parameters are important. Here you see A. So A is the plastic deformation starting from yield till capping point C. So till the strength degradation occurs. This A is actually chord rotation theta. So this chord rotation, which is given in radian, this is important. This property B, which is the value of rotation again in radian till collapse. So this value of A, B, and C is the residual strength as a ratio of yield strength. So if yield strength is 1 unit, this C is a fraction of that. Because this is normalized curve, it is divided by the yield strength. So this value actually is representing the yield point, and the corresponding strength is yield strength. So value of A, B, C, this is important. And what AC41 gives us, first the cracked section stiffness of different members. So in case of beams, it is 0.3 times the gross stiffness, EC into IG. And here you see ECE. So this E stands for expected strength. And expected strength is FCK plus 1.64 sigma. So you remember how we obtained the characteristic strength? The characteristic strength is obtained by mean strength minus 1.64 sigma. So expected strength, which is the mean strength, is characteristic strength plus 1.64 sigma. So in case of nonlinear analysis, we will be using expected strength, not the characteristic strength, because here we are not using any factor of safety on strength. We will be using factor of safety on deformation capacity, on inelastic deformation. We will be controlling inelastic deformation. So we don't need any factor of safety on strength, because strength in any case is to be exceeded by the earthquake. In case of column, it is 0.7. And if the column is lightly loaded, the axial force is less than 0.1 ag F-CE. F-CE is actually cylinder strength. So expected cylinder strength. So if it is less than 10% of that, then this is 0.3, same as in case of beam. And you remember 13920 also says that if the axial force in column is less than 0.1 times Ag into FCK, then we can detail it like a beam. Otherwise, we have to detail it like a column. So the stiffness changes beyond 0.1 AgFC. Like that, the stiffness for shear walls, beam column joints, all that is available. So using this, we can model our members in a frame building or frame shear wall building. So for example, this is a beam which is connected by the columns. Beam we can represent by, again, it will be bending during earthquake in double curvature. So we can represent it by two cantilevers. The portion between these hinges we can consider as elastic, and all the plastic deformation we are assuming to be lumped here. And this LP is the length of the plastic hinge length, and the hinge we are assuming at the center of this plastic hinge length. And we can assign the backbone curve to this. Initial portion of that backbone curve can be obtained from section analysis. Remaining portion is to be obtained from ASC 41 or ACI 369.1. So this is one option. And the software commonly used is ETABS or SAP. And after my lecture, one of my PhD students, Mr. Tajul Islam, he will demonstrate you pushover analysis of a building using software ETABS. So there you can assign this backbone curve. Another alternative method is also available, which we will be using for columns. That is fiber hinge. So in fiber hinge, what we do, the whole section we divide into a number of fibers. Those fibers consist of concrete fibers or steel fibers, and we assign stress strain curve of that material of which this fiber is consisting of. For example, to a concrete fiber, inside the ties, inside the stirrups, we will assign the stress strain curve of confined concrete. To a fiber outside the stirrup, which is unconfined, we will assign a stress strain curve of unconfined concrete. To steel, we will assign the stress strain curve of steel. So we will assign these different stress strain curves, and section analysis will be done by the software automatically. So this hinge is not covered by ASC 41, but you can use the options available in ETABS, and some more parameters you will require if you are doing nonlinear time history analysis. But if you are doing performance-based design using pushover analysis, the simplified analysis which we are discussing today, then you need to define these stress strain curves of steel and concrete. Now, ASC 41 gives this type of tables, that is performance acceptance criteria, modeling and performance acceptance criteria. And here you see the values of A, B, C and IO, LS, CP. The values corresponding to IO, LS and CP in the member, immediate occupancy, life safety and collapse prevention, we discussed earlier as the structural performance labels. So the value of theta, chord rotation, corresponding to IO, LS and CP. You see the value of A till there is drastic reduction in the strength of beam, this value is 0.025 radian. And B, where the collapse occurs, it is 0.05. And you can see that the value of CP is same as value of 0.05. So if the plastic rotation exceeds 0.05 radians, the collapse of that member, that beam, will take place. Then the value here for life safety, okay, this is corresponding to A. So this A is before there is loss, that drastic reduction in the strength. So before that capping point. So LS corresponds to that capping point. So if the plastic rotation is less than the capping point, it is corresponds to life safety. Then you can see that this value of IO, LSCP and ABC depend on three parameters. One is this rho minus rho dash by rho balance. This is showing the extent of under reinforcement in the beam. So here rho is the tension reinforcement, rho dash is the area ratio or volume ratio of compression reinforcement, and rho balance is the ratio of balance reinforcement. So rho minus rho dash by rho balance. And you have to keep in mind, in case of earthquake, the moment is reversible. So the top reinforcement will be in tension and bottom in compression for one direction of earthquake, and for the other direction of the earthquake, this will reverse. The top reinforcement will become compression reinforcement and bottom reinforcement will become tension reinforcement. So in one case, rho minus rho dash will be positive, and another case, rho minus rho dash will be negative. So rho minus rho dash by rho balance less than 0 means that it is negative. The tensile reinforcement, this is the tensile reinforcement. So tensile reinforcement is smaller than the compressive reinforcement. So this will happen when the beam near the joint is in sagging. Tension is at the bottom. So in case of a beam which is framed into the column, the reinforcement at the bottom is less. So when the tension is occurring at the base or at the bottom face of the beam, then this will be negative. And when it is occurring, tension is occurring at the top, this will become positive. So rho minus rho dash by rho balance less than 0, this value will be more. When rho minus rho dash by is greater than 0.5, you can see that this value reduces. From 0.05, it reduces to 0.03. Then the second column here, it is representing conforming and non-conforming. Conforming means as per ductile detailing code. In our case, it is IS 13920. So if the detailing is done as per IS 13920, then these rows will be used. If ductile detailing is not done, means OMRF, then in OMRF frame, this will be used. In SMRF frame, this will be used. When we are doing the design of a new buildings, then we will be using SMRF in most of the cases, except zone 2. But when it is existing building, then any of the two situations may be there, depending on the design. And then this third column, it is giving us the shear capacity ratio. So V is the applied shear and BWD is square root FC dash. This is the shear capacity. So BW into D, BW is the area of the web into D, BW into D, BW is the width of the web, D is the depth. So this becomes the area of the web multiplied by square root FC dash. Square root FC dash is a measure of shear capacity. So the denominator is the shear capacity, numerator is the shear demand. So ratio of this demand to capacity, that is also important. So, and it is given in 2 units. 3 is in FPS unit, and in case of SI units, for our case, this is 0.25. So if it is less than 0.25, then the value will be larger. If it is greater than 0.5, then the value will be smaller. So if the shear demand is more, then also the ductility is going to reduce. If the compressive reinforcement is more than tensile reinforcement, then also still it is under reinforced, but the ductility is going to reduce, and so on. Now in ASC 41 2013 for columns, similar values are given. IOLSCP. Actually, there was slight change. So this is the table. Actually, it is given like this. So in case of 2017, and now it has been further revised in 2013. So many revisions have come. So currently, it is similar equation. And now these equations have been transferred to ACI 369.1. But if you look at AC 41 2017 version, these are available in AC 41 itself. So value of A, B, C, etc. are given like this. Expressions are given. Rather than numerical values, for columns, they have given continuous expressions. And then the value of IOLSCP you can get in terms of A. and B and C. So value of A, B, and C are given like this. So the idea is that based on these parameters, NUG, this is the axial force under gravity load, BU is the shear force. Okay, this is the gross area AG multiplied by F dash CE, and then the shear capacity of the column. So expected shear capacity of the column. So this is the shear ratio. So, and this is the tensile, or sorry, not tensile. In case of column, it is the total reinforcement ratio. So reinforcement ratio, axial force ratio, and the shear capacity ratio. Based on these three ratios, which were earlier in case of beam or earlier versions of SC41, those were given in tabular form. Now those are given in the form of an equation. That's the only difference. So coming to a practical building, how we are going to analyze that. So first we have to make a model. And when we are making of a model, we have to assign some plastic hinges. Rest of the model will remain same as you have been doing in case of conventional analysis. Additional parameter here is assigning these hinges. So typically these many hinges are required. So in a beam or a column, at each joint, there is a flexural hinge. So on both sides in the beams, both sides in the column, we will require flexural hinge. In case of a beam, it will be moment hinge. In case of a column, we have to assign a PMM hinge, because in column, there will be interaction of axial force with the moment. So either we have to assign a PMM hinge, or we have to assign a fiber hinge, as I discussed, where the cross section is represented by a number of fibers. And then if there is a possibility of yielding of the joint, if the joint is not protected using capacity design method, the code provides the method to protect that. So if the column, beam column joint is made stronger than beam and column, then we don't need this hinge. Otherwise, we have to assign this hinge also. Similarly, in beams and columns, we need to assign shear hinges. So this rectangle, I'm showing the shear hinges here. So these shear hinges again are not needed if we follow the capacity design and we ensure that the beam and columns are not going to fail in shear. Those are going to fail only in flexion. Shear capacity is more. Then the shear hinges are not needed. Otherwise, we have to assign these shear hinges also. So in case of existing buildings, we do not know whether the capacity design has been done or not. So there we will be assigning these shear hinges also. And shear hinges do not have any ductility. So these are also called force controlled hinges. As soon as the force demand, shear force demand in the member will reach its capacity, and shear capacity we can calculate using the expressions given in codes, IS 456. So as soon as it exceeds that value, the failure will occur. In case of moment hinge, flexure hinge, it is a displacement controlled phenomena and it has ductility. As soon as the yield strength is reached, failure will not occur. The plastic rotation will start. But in case of shear, as soon as the shear capacity is reached, the failure will occur. So that's the difference between flexural and shear hinges. And in case of ductile detailed frames where capacity design is followed, shear capacity or shear failure is protected by capacity design, this hinge is not necessary. Similarly, in case of shear wall is like a cantilever column. So the hinge formation will take place at the base, and we will assign either a lumped plastic hinge here or a fiber section lumped plastic hinge. Two types of hinges we can provide. ASC41 provides the values of A, B, C for lumped plastic hinges, similar to beam and column we have seen earlier in the similar manner. This is also here. This is the ratio of the shear capacity and whether the ductile detailing is done. Ductile detailing in case of shear wall means that the confinement in boundary elements has been done or not. So that will be seen. And here the axial force, P is the axial force, and this is the reinforcement. So whether this relationship is followed or not, accordingly we can calculate ABC, IO, LS, and CP, and we can assign these hinges to the shear wall at the base. Now the software ETABS or SAP, that provides a facility in which that command is called auto hinge, in which it automatically uses these values. But what we have seen that it is not following the code properly. So even when you are using auto hinges, be careful, check those auto hinges using the code, corresponding code, that it has taken the value of ABC and IOLS and CP as per the applicable case. So you have to see which case is applicable for your building, and corresponding values of ABC, IOLS, and CP you will use. Okay. When we are using fiber section, then we are applying stress strain curve, we are assigning to the material, but this in stress strain curve, we need to consider the reverse cyclic behavior by curtailing the ultimate strain. So under the monotonic load, under the monotonic test, the strain in steel will be much larger. But under cyclic load, that strain will be reduced. That reduced strain is called usable strain limit, and ASC 41 provides the usable strain limit. For compression fiber of concrete, it is, if it is unconfined, it is 0.002. If it is confined, then it is 0.02. And in tension, the maximum strain we can allow is 0.05. So you remember IS 13920 gives a minimum elongation of 14.5%, but that 14.5% is under monotonic load. Under cyclic load, it will fail under much less strain, only 5%. So we allow only up to 5% to take into account this low cycle fatigue. So when it is subjected to large number of cycles, even at such low strain, it will rupture. Now, when we are using fiber hinges, then we need the performance criteria also in terms of strain, because we will not get plastic rotation or chord rotation, and that's why we have to use this strain. And these values we have taken from different codes, and for actually ASC 41 does not provide this. So this we have taken from other codes, and corresponding to IO, LS, and CP, the permissible strain in concrete and steel is given corresponding to different performance levels. When we are defining the acceptance criteria in terms of interstory drift, then interstory drift for different types of structures for IO, LS, and CP, that also we have compiled. Again, ASC 41 is not giving, but the earlier documents, FEMA 273, which was the first document for performance-based design, there this was done. This was provided. We have taken from FEMA 273, but now it is believed that interstory drift is not a good criteria to assess the performance. So that's why ASC 41 has dropped the interstory drift, but some of you may like to use interstory drift still. So this we have compiled from FEMA 273. Then one other problem, very common problem in Indian context, is masonry infills. That invariably our RCC buildings will have masonry infills. So in masonry infills, we can represent the infill by a diagonal strut. So this is the diagonal strut, and it will be provided a slightly eccentric strut here, so that whatever shear force is occurring in this column, that can also be represented. It requires defining of another hinge and another node first here, then hinge and shear here. So it's a little bit complex. So most of the time what people do, they join it with the diagonals. So in place of eccentric diagonal, they are using concentric diagonal strut. And if we are having partial infill, then we can use partial height infill, then also we can use this. And expression for effective width of this strut are available in ASC 41. And that's how the model will look like when we are modeling this concentric diagonals also. So here infills are modeled with these concentric diagonals. And this is the flexural hinge, this is shear hinge. So shear hinge will not be required if we are sure that the shear failure is not taking place, is not going to take place. You have protected the shear failure using capacity design, then this hinge is not necessary, but flexural hinge is needed. Similarly, in case of beams, we are providing flexural hinges. Now, a three-strut model for infills, a trilinear model for the masonry infill is given. So this initial stiffness, the yield strength, the peak strength, post-peak stiffness, these parameters are available in ASC 41 and now in ACI 369.1. So depending on the aspect ratio and strength of frame with respect to the strength of infill, you can get these values. Again, IOLSCP values are given. So that's the background. Now we are having 10 minutes remaining, and in these 10 minutes, I will tell you how the pushover analysis is done. So in pushover analysis, we will be needing all this background which we have discussed so far. We started from material nonlinearity, the stress strain curve of material. Then we developed the section nonlinearity, that is defined in terms of moment curvature. Then we did displacement, force versus displacement behavior of the member or the member ductility, which is defined by force displacement curve. And then we took into account the cyclic nature of earthquake, because that causes deterioration of strength, stiffness, and ductility of the member. So that we have taken from experiment. Now, using those values which are given from experiments in ASC 41, we can assign hinges to the beams, columns, shear walls of our building, RCC building. Then we have to perform analysis of the building. So for analysis of any building, as I discussed earlier also, 4 methods are available. Linear static procedure, where the force is considered static and the behavior is considered linear. Linear dynamic procedure, either response spectrum analysis or time history analysis of the linear structure. So these are used in conventional analysis. For performance-based design, we are using nonlinear static procedure, the pushover method, which we are going to discuss. This is an approximate method, but simplified. The more accurate method or the most rigorous method is nonlinear dynamic procedure. The problem with nonlinear dynamic procedure is that it is based on time history. Nonlinear static procedure can be used with response spectrum, whereas nonlinear dynamic procedure is to be used with time history, and selection of time history itself is a complex task, and then it requires a lot of computational effort. Nonlinear static procedure or pushover analysis is much faster, much faster as compared to nonlinear dynamic procedure. It can be done in few minutes. This may require a few days or weeks or maybe months also. If the structure is really large, then this can require months to run. So this is quite time consuming and complex. That's why the pushover analysis is a little more attractive, but we have to keep in mind this is approximate method. So how we perform pushover analysis? So let us say this is the building. We make a conventional model like we are doing in current design philosophy. We make a model by representing all the beams, columns, shear wall by structural elements, developing stiffness for those, and then we apply a lateral load. And this lateral load, this has to be distributed along the height, and the distribution along the height we take proportional to the fundamental, the mode which is having the maximum contribution. So that's why this pushover analysis, which is also called nonlinear static method, it is also called single mode method, because here we can consider only single mode shift. You know, in dynamic analysis of a building, more than one mode are participating. So there is contribution of higher modes also. But in pushover analysis, we take the load distribution corresponding to fundamental mode only. And this can be either linear or parabolic, depending on the height of the building. And we distribute the load along the height. We do not know the value of the load. So we will take any arbitrary force and we will distribute along the height. And total force will be given as base shear. So base shear is nothing but summation of all the floor loads here. And then I will apply these loads. And if I gradually go on increasing this load, so I will have certain displacement at the roof. And you know, with conventional modeling, where I have not assigned any plastic hinges, the load displacement curve will be linear. As I have shown earlier, it will continue till infinity. But in real structure, it will not be like this. In real structure, if I assign the plastic hinges, some hinge will yield, some plastic hinge will form. Now, where the plastic hinge will form, that will depend upon the demand to capacity ratio. Where the demand is exceeding my, the yield moment capacity, first, there the first plastic hinge will form. So if I go on increasing this load, let us say here the first plastic hinge is forming. And when this plastic hinge is forming here, the moment value here will be equal to the my value of this hinge. So wherever that first hinge will form, corresponding to that, it will calculate this base shear VB1 and corresponding displacement delta 1. Till this, its behavior is linear. The behavior will be given by the conventional model. But when this plastic hinge forms here, now the behavior of the structure will change. This plastic hinge will act now as a release for additional force. So when we are determining its behavior under additional force, it will be like a structure with a release here. And due to that, its stiffness is going to reduce. So we can see that the behavior will be given by another straight line, but the slope of that straight line will reduce because it is representing the reduced stiffness. And again, it will follow a linear load displacement behavior till another hinge forms here. So when the next hinge will form here, corresponding to this value of base shear BB2 and the displacement delta 2, it will follow another linear path, which is having a stiffness corresponding to one release. Now there are two releases. So for further loading, the slope will reduce further. And we will continue this process till either the structure becomes a mechanism. When the structure will become mechanism, when all the hinges will form here in the beams, and finally the hinges will also form in the column. So we know that this is an indeterminate structure, and its degree of indeterminacy is such that it can sustain plastic hinges in all the beams. And then when finally the hinges form at the base of the columns, then it will become a mechanism. And once it becomes a mechanism, it will not be able to take any more load, any more additional load, and it will go on deforming. And the building, before applying this load, was also subjected to gravity load, the dead load specifically, and a percentage of live load also. So due to that gravity load, there will be P delta effect. And due to that, the stiffness will become negative after a point. So when it becomes a mechanism and P delta effect is there, so its stiffness will become negative. That means the load displacement curve will slope downward. And if we continue further, now it will not be able to take more load, rather it will drop some force here. So force dropping will take place. And finally, one of the member here will reach its collapse, or the structure as a whole may collapse. So collapse can occur either globally when the whole structure becomes unstable, or any member here that collapses. That is local failure. When the member will collapse? When the plastic rotation at that member reaches point E, or value corresponding to Cp, which we have seen from the backbone curve. So if that value of plastic rotation is reaching, we consider that as the failure or collapse of the structure. Now this curve is important. This is backbone curve of the whole structure, or the capacity curve. We call this as the capacity curve. So this curve is having three informations about the structure. It is a signature curve of the structure. And what this signature curve is showing? It is showing the initial stiffness, it is showing the yield, and it is showing the ductility capacity. And using this curve, we can determine performance point or the realistic value of response reduction factor R, which we can use in our design. How we do that? There are different methods. So first, the capacity curve. This capacity curve is converted into capacity spectrum. How we convert this into capacity spectrum? We had plotted it in terms of base shear. Base shear we had taken on the y-axis and roof displacement on the x-axis. Roof displacement and base shear can be related with SD, spectral displacement. So spectral displacement we obtain using this relationship. Spectral displacement is roof displacement divided by participation factor of fundamental mode. PF1 is fundamental mode participation factor, and phi1 at roof is the coefficient of fundamental mode at the roof. So if we multiply these two factors and then divide roof displacement by this participation factor into phi1 roof, we will get a spectral displacement. So similarly, the base shear we can convert into spectral acceleration using this relationship. And now we can compare it with the demand. So demand is given in terms of response spectrum, I told you. So this is the response spectrum, demand response spectrum corresponding to 5% damping, because in the code it is given corresponding to 5% damping. And this is our capacity curve or capacity spectrum. We have converted this into SA versus SD. So both the demand and capacity are converted into SA versus SD. And when we convert this into SA versus SD, we call it spectrum. When it was base shear versus roof displacement, we were calling it capacity curve. Now it is capacity spectrum. And we can compare the only issue in comparison is that this response spectrum corresponds to a given damping, and that damping is 5% in the code. Whereas along the demand curve, the damping changes. How the damping changes? Because at different displacements, at different points here, the size of the hysteretic loop goes on increasing. So larger is the size of the hysteretic loop, more is the equivalent damping. So we have to convert that into hysteretic damping, and then we can convert it into equivalent viscous damping. And once we know the equivalent viscous damping, we can reduce the demand curve. The response spectrum we can reduce using those damping factors. Maybe you are familiar with those damping factors. Our code IS 1893 part 1 was giving earlier. Now IS 1893 part 4 is giving those factors. So for higher damping, the response spectrum is lower. Spectral acceleration is lower. So with the increased damping, we can reduce it. And we do this iteratively so that the reduced response spectrum, the reduced demand curve, reduced demand spectrum is intersecting the capacity spectrum at a point which has the same damping. So the damping goes on increasing here. We choose a point here such that for the damping, corresponding damping here, if we reduce the demand curve will intersect it here. So this point we call performance point, and the corresponding displacement, we will read SD from here and SD we can convert into delta rho using this relationship. We can we can convert SD into delta rho. So we know the displacement. And one more thing, when we were doing pushover analysis, we were considering these hinges. So at each point here, we were determining that how much plastic rotation has occurred at already formed hinges. So whenever a step in the force was taken or displacement was taken, there was some plastic rotation occurring at the hinge. And we were keeping a track of that plastic rotation also. So we know that what is the status of the hinge. This is the first hinge forming. So first hinge has yielded here. Here the second hinge formed. Here the third hinge formed. So maybe here the first hinge might have reached immediate occupancy. Then maybe here the first hinge first hinge might have reached life safety. And here one of the hinges is reaching collapse. So it is collapsing here. So from this performance point, I can see what is the performance of my members. So none of the members has crossed IO. First IO is occurring here. So I know that this is the performance of this structure is immediate occupancy. So that's how we determine the performance point using pushover analysis. This is an iterative method. ASC41 provides a direct computation method also, which we call displacement modification method. So in displacement modification method, the roof displacement delta T corresponding to a given response spectrum can be obtained directly using these coefficients C0, C1, C2, SA, T square by 4 pi square G. I will explain these one by one. So C0 is a modification factor which relates the response of single degree freedom system to multi-degree freedom system. So actually response spectrum, any response spectrum is giving us the response of a series of single degree freedom system corresponding to their period. Now here we have a multi-story building. Multi-story building is having a multi-degree freedom system. So we need to relate the response of the single degree freedom system with multi-degree freedom system. So this coefficient C0 comes into picture, and this C0 is same as I discussed earlier here, this participation factor into phi1 at roof, and this we do for fundamental mode. So that is C1. AC41 actually gives a table also. If we do not have the mode share, using that table, we can calculate this C0. Then C1, this is the modification factor which relates the displacement of inelastic structure with the elastic structure. Response spectrum is giving the response of elastic single degree freedom systems. Here we have an inelastic system. So we have to relate the two. Again, SC41 provides an expression using which we can do. But one thing is interesting, that when the period is greater than 1 second, T1 is unity. This is the so-called displacement, equal displacement principle. So as per equal displacement principle, for long period structures, and long period means greater than 1 second, the displacement of elastic and inelastic structures are same if their periods are same. So that is represented here by C1 equal to 1. For less than 1 second, C1 can be obtained using this expression. Tajul will again explain you how it can be done. And then we can calculate C2. Okay, so C2 is given by this expression. And once we know C0, C1, C2, we can calculate the delta roof like this. Once I know this roof displacement, I can go back to my original capacity curve, and corresponding to any roof displacement, I can see what is the performance. For example, if my roof displacement comes out to be here, then I know that the performance is somewhere between IO and LS. If the roof displacement comes here, then this is between LS and CP. So we call it life safety performance. If the roof displacement is here, then this is immediate occupancy performance. So like that, we can obtain the performance of the structure using this simple monotonic analysis, considering cyclic nature of the earthquake approximately using backbone curve or backbone curve parameters, which are given in SC 41. So we are using those backbone curve parameters, which have been obtained from cyclic experimental studies. So those we are using, and in place of time history, we are using response spectrum, either using this method, iterative method, which we call capacity spectrum method, or using this displacement modification factor, displacement modification method of ASC 41. We can obtain the roof displacement using response spectrum. And once we know the roof displacement corresponding to performance point, we can get the performance of the structure. So that's all. That's the background for this pushover analysis or performance-based design using pushover analysis. We will have the break, and after the break, when Tajul will demonstrate you one building, then you will understand it more clearly. Thank you. So I will stop sharing my screen.
Priya already there? Hello.
So I think
Yeah. I think you can.
We can break.
You can break. Right now it is 5:10. We can take 10 minutes break and we can join again at 5:20.
5:20. Okay. And Tajul has already joined. So
Yes,
I will
Taj.
request him to take up at 5:20, and he will demonstrate whatever steps we have discussed now. He will demonstrate on an example.
Yeah. Fine. Perfect.
Thank you.
Thank you.
We will meet after 10 minutes.